Hey, good morning, everyone, and welcome back. I hope that you can hear me, and I also hope that all is well. As you can see, I'm in slightly different environment, long story. Uh, Before I start, I have to warn you, there is a serious danger today that I may be going too fast. I guess there is always a danger that I may be going too fast, as you may have noticed. But today in particular, I tend to think of the material that I'll be presenting as basically trivial consequences of the theorem that we proved last time. And I know consciously that is not true, but still I may just basically rush and say, oh, well, this is obvious, this is obvious. If you notice this is happening, please do slow me down. And actually, I just noticed one sign that I am already going too fast. This wasn't on purpose. Today is January 22nd, I think. I am already tomorrow. So anyway, on the first slide, basically, you have the most important theorem from last class and today's class. I'm just trying to arrange the windows so that I can see both chat and what is on the screen. So theorem that we proved last time. Now, since at the end of the proof I sort of rushed it, I just wanted to go over it quickly, just once again, so that we know what's going on. So, right, theorem is that if you have a sigma unital, non-unital cyst algebra A, then its corona is countably degree 1 saturated, and what one needs to prove? Well, you have this sequence of conditions of this form, and pk is a polynomial which is of degree 1 in variable x. As I said, we can have any number of variables. Proof is virtually identical. And we assume that this sequence of condition is approximately satisfied in this corona. Which means that for every finite subset, for every epsilon, there exists some Bn, which satisfies first n conditions up to 1 over n, say. And then we choose this approximate unit, En, which is quasi-central, which means that it commutes with any countable set given in advance as much as we want. And now we form these Fn's. Remember, Fn was En plus 1 minus En square root of that. So that sum of the squares of the Fn's is equal to 1. And then we chop up these witnesses for satisfying finite segments of the type by using Fn's in this way and form this B tilde. Remember, P is the map from the multiple algebra into the corona. And the point is that this B tilde works. Now, before claiming that it works, we have to check that it belongs to the multiplier algebra. And the point is that norm of the quotient, actually norm of B tilde itself is less or equal than the supremum of norms of B and tildes. And remember, for this, there was this little trick that I used, which uses C star equality and matrices. In the book, this is done by using a unital completely positive maps, but you don't even need to know what that is. So basically, there is a more elementary proof. Right, so we are sure that this B tilde exists, that this series on the right-hand side converges in strict topology. And moreover, and now this is the point where we use the assumption that these are all degree 1 polynomials. If you compute pk of B, it is up to an element of A equal to this here, sum of Fn to 1/2 pk tilde of B. This should be bk, not bn, because actually no, that's what I wanted. That's what I wanted. Bn in A. So the values of these polynomials are almost equal here. And now, the punchline is that we actually want to check that if we evaluate kth condition at P of B tilde, we get the right value. Right, the right value is RK, R for right, I guess. Now, there are two parts in proving this. We don't want it to be too large, we don't want it to be too small. And proofs are quite different. So you see here it is, right? So this is the norm, the value. So we need to prove that it's equal to lim sup of these. And the reason why it's less or equal is, again, this trick with matrices. Right? So keeping it small is reasonably straightforward. Now, keeping it large enough is slightly messier, still not difficult. Remember, what I did is represent A faithfully on some Hilbert space, and then we chose those unit vectors Cn, which witnessed that norms of these elements are as required. And there was a little argument showing that you don't need to worry about anything but the value in the right place. So we bumped it up to the right moment. So anyway, I repeated all this because I wanted to point out that it is absolutely crucial that these are all degree 1 conditions, that even if you have a quadratic polynomial, this is not going to work. But still, this does give us a lot of mileage. So let's take a look at the applications. And as I said, there are quite a few applications, and I may tend to rush those, so please do slow me down. So basically, here I have a standing assumption, capital C is the corona of some sigma unital, non-unital C algebra. That algebra is not even important. It's off the radar now. We don't even care what that is. All that we care is that C is countably degree 1 saturated. And there are many other countably degree 1 saturated C algebras. And first, what I would like to do is go over those examples that I mentioned exactly a week ago as a motivation for the introduction of degree 1 saturation. So here is the first one. It has a name. I didn't mention it a week ago. It's called SAW star, which is a very silly name, so I'm not going to discuss it. It's a very funny acronym. It was actually, I think, concocted as a joke, so never mind. Here is a statement. If A and B are separable C star subalgebras of C, and A is orthogonal to B, so what that means is that if you take anything from A and anything from B, the product is equal to 0. Then you can separate them. There exists C in this big algebra, which has the property that it acts as a unit on A. This is what it means basically, right? So you multiply any element of A on the right by C, you get it back, and it annihilates B, but if you multiply on the left. Okay, so all that we need is just to write down what is the right type, and then check that type is approximately that it's satisfiable, and then degree 1 saturation does the job. So what is the type? T of X. Well, let's see. So we need to know that A times C is equal to A. Also, we're just taking norm of AX minus A is equal to 0. If I'm not going to write equal, I'll just write colon here so I don't have to write the curly brackets. So I look at all conditions of this form where A is an arbitrary element of A. Second, I look at all conditions of the form X times B in norm is equal to 0, where B ranges over B. Right, so if X satisfies this type, we are good. This X, we just call it C, and it has the properties that are required. Now, there are two things to do here. Remember, this is notion of countably degree 1 saturated. There are uncountably many conditions here. However, that's okay. These are all continuous functions. We can just, instead of letting A range over all of A, just range over some countable dense subset of A. Right, so I can just call it A0, where A0 subset of A is countable and dense. And here, B0 is subset of B. I have to say that some people don't even bother doing this, picking these countable dense subsets. You just define notion of separable type, which is not completely obvious, but you can sort of guess what it should be. And then instead of countable degree one saturation, just think of separable degree one saturation. So every consistent separable type is realizable, but I'll just stick to this. Okay, so this is countable type, and all that we need to do is check that indeed T is approximately realizable or satisfiable. Sorry, I just keep on changing my mind about what is the right word. So T is satisfiable. Now, what does that mean? Well, we choose a finite subset of T. So fix T0, and I like to use this notation that operator algebras use for finite subsets. So this means that T0 is a finite subset of T, and also choose an epsilon greater than 0. So I have finitely many conditions of this form and finitely many conditions of this form, and need to satisfy this approximately. But now remember, A is a C-star algebra, so it has an approximate unit. I basically, all that I need to do is go far enough in the approximate unit. So fix an approximate unit, En, A is separable, right? So it's going to be countable for A. And now, this one? No, this one. And now just fix N so that En, actually, no, I don't want that, such that AEN minus A is less than epsilon for all A occurring in T0. Right, what I mean by this, well, T0 is a finite set. It can mention only finitely many elements of A. So I can assure this. You may object that I'm doing this on the right. We were always using approximate unit on the left, but ENs are self-adjoint. Right, so there is really no difference. This is just the same as saying that En A star minus A star is less than epsilon. So it doesn't matter what side you're acting on. You can even act on both sides. It all works. Right, so fix N. But okay, so En satisfies one part of our T0. But then what is En times B? Well, En belongs to A. And A is orthogonal to B, they annihilate each other. So En B is equal to 0 for every B in B, right? Which means that En approximately satisfies T0. Approximately satisfies T0 up to epsilon. So T is what is satisfiable. Okay, and by saturation, there is T is realized. Realized in C, and that's all we wanted, right? So T exactly describes C as required. So you see, all of these proofs look like this. You just figure out what the right type is, check that it's consistent, and then just conclude. Well, that's it. All right.
Well, sorry, Ilijas, I just wanted to mention that I think that in the definition of SAW, sorry, algebras, it's a little bit stronger. You can allow A and B to be in sigma unital, which same
difference. It makes no difference because you just look at hereditary closure. It's equivalent. And no, since I'm not defining it, it's an easy theorem that's equivalent. But yeah, thanks. So Said actually has a paper. I'm going to mention it later on. Very nice result about these algebras. So I just said that acronym is silly. It's not that notion is silly. Right. Okay, thanks. Right. So here is the next example. Now again, yet another acronym, CRISP. R stands for Rees separation property. So it's very similar to the previous one, but there is a difference. So what do we have here? We have two sequences of elements in C+, so they're all positive. And ANs form an increasing sequence, BNs form a decreasing sequence, which sits on top of them. So they're like, I mean, set theorists would call this omega-omega gap, right? So they're approaching to each other. Then there is a positive C such that C interpolates this pre-gap. Now, story is very similar, except that the natural conditions are not degree 1, or not obviously degree 1. So you see what the type should be. Well, something like AN is less or equal than X, and X is less or equal than BN for all N in N. Right, so this is going to assure that X is positive, and if X realizes this, it would be as required. However, this is not a degree 1 condition. It doesn't even look like a polynomial, right? Right, so these are not degree 1 conditions. Right. So what do we do? Well, basically, there is a little trick which is very useful, and it is sort of a template for other tricks. You see, our syntax allows degree 1 conditions, but we can get much more mileage from there. There are other conditions which are equivalent to being, which can be, I mean, there are notions that can be expressed by using degree 1 conditions. So that is the lemma. So I just realized that maybe I have it. Yes, I have it here. Right. So here is the lemma. Now I wrote here proper subset. There is more in lemma 15.2.9 than what I need right now. So you may take a look. But basically, what we need is that condition X greater or equal than 0 is equivalent to a degree 1 condition. And that's really all that we need from here. Sorry for being so clumsy. Oh, no. Okay, so I just added 2 unneeded pages. Let me try here. Right, okay. So what is the trick? Well, so first, we want to say that X is self-adjoint. Right, X is equal to X star. Of course, this is not degree 1. I mean, if you're really picky, you can say, well, but that's not degree 1. But if you just write it in this way, norm of X minus X star equal to 0, then it is degree 1. So being self-adjoint is equivalent to degree 1 condition. Now, what about greater or equal than 0? Well, so if we know that the norm of X is bounded above by some constant K, and most of the time constant K is going to be 1 in my here, because we did require elements that satisfy type to belong to the unit ball. So if X is less or equal than K and X is self-adjoint, then X is greater or equal than 0, if and only if the following holds, the norm of the operator k minus x. Here I identify scalar k with the k times the unit. I'm thinking of unit Alceste algebra. So if and only if the norm of k minus x is less or equal than k. Right? Why is that so? Well, it's really a picture. So what does x look like? X is, by continuous functional calculus, it is some real valued function. So continuous functional calculus. Here is our k. Right. So what is k minus x? Well, it is this distance here. So you see, if the function, if the graph of x stays above the x-axis throughout, this is less or equal than k, always. Right? You're looking at sup norm. But if x drops below 0, then this is greater than k. Right? So this is the culprit here. And now this here is again, let's see, norm is less or equal than k. So I wanted it equal to k. Oh yeah. There is one more trick. There is one more trick that you see. I forgot about this. So you see, we got that now we can reformulate our. Let me just see. Yeah. Okay. Okay. So there is another compactness argument. So that I forgot about, as I said. What is the trick here? So I can write down this pseudo degree 1 type, which describes this situation. So let me see. Oh yes, also another thing is the following. So lemma implies that an, oops, an less or equal than x, it is equivalent to x minus an is greater than 0, and that's equivalent to norm of k minus x minus x and an is less or equal than k. Now, what is k here? Well, I can just take, for example, k to be the norm of b0. Right? I know that an is less or equal than blah, 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 and x is less or equal than b0. So definitely this difference, and these are all positive elements. So these are all going to be less or equal than that k, right? I need the concrete k. I cannot use norm of x here. So I can. So in stage 1, I can reformulate the type that I need in these terms, right? So we have a type under quotation marks, right? K minus, actually this is minus x plus an less or equal than k. And also what I want x less or equal than bn, right? Which is bn minus x greater or equal than 0, right? So that would be norm of k minus bn plus x less or equal than k for all n in n. Right? So this is my type. There are countably many conditions. And now, first, this type is approximately satisfiable. Let's not worry about the fact that it's not a degree 1 type. Let's just ignore that fact. So so this type is approximately satisfiable, right? Basically, by an for large enough n, right? If I plug an into these, if you give me any finite number, so here are a1, a2, right? Ak, here is b1, b2, bk. If I choose an large enough, it is greater than all of these, and it's less than all of these, so it satisfies these conditions. Now problem is that I don't have degree 1 type, but now look at the following. Basically, there is a little compactness argument. So as n approaches to infinity, look at the following. Norm of k minus an plus a little k is fixed. And the other one, k minus b sub little k plus an. These are two bounded sequences in a compact interval in the reals. So I can go to a subsequence by a Heine-Borel theorem and make sure that sequence converges. So we can go to a subsequence so that this converges to something. Let's call it sk, and this calls let's say s0k, and this is s1k, right? And now I have my data for what the right type is. So I can just use these numbers. So finally, the type k minus x plus a little k is equal to s0k, and k minus b little k plus x is equal to s1k. This is degree 1 type. It is satisfiable, and its realization does what we want. So
when you say satisfiable, means for every finite subset, for every epsilon, I can get as close to.
Right, exactly, right, which is right, because you have convergence. So I should be saying approximately satisfiable. Thanks. It's approximately satisfiable. Thank you. I should have, yeah, thanks, Matteo. Right, okay, so I have to admit that I forgot about this part of the proof. So this was a little bit longer than necessary, but okay, you see, sometimes one has to go through some hoops, but let's take a look at, oh yes, right. So here is a question that I don't know the answer to. Basically, some sort of analog of lemma is x is a projection equivalent to a degree 1 condition. You see, being projection requires you to have that x minus x squared, the norm is equal to 0, which is not degree 1. So it's not obviously degree 1, but we'll see some other examples later on that it's not really hopeless. That there are conditions which are not obviously degree 1, but can be restated, recast as degree 1 conditions. So if the answer to this question is positive, that would mean that whenever you have a type, so that its finite subsets can be approximately realized by projections, then type can be realized, entire type can be realized by projection. So in particular, in statement like this, crisp if you could approximate finite pieces by projections, separate finite bits by projections, you would be able to separate the whole thing by projections. And I don't know whether it's true or false. Right, so next one. So again, C is a corona of degree 1 saturated algebra. Now here we have a positive element which has 0 in its spectrum. Then the annihilator of A intersected with C is not 0. So there is a non-trivial element which annihilates A. And now what is the type? Well, it just says that norm of AX is 0. And well, okay, so this is satisfied by 0 trivially. But you also want to say that X is non-trivial. And you see, because annihilator is a C-star algebra, it has elements of all possible norms. So why not say that norm of X is 1? So you see, this type has only 2 conditions. And to somebody who is experienced with classical discrete model theory, type with 2 conditions is either satisfied or it's inconsistent, end of the story. In continuous logic, that's not the case because we're talking about approximate realization. So it could be that this type is approximately satisfiable in some C-star algebra. Actually, in inseparable infinite dimensional C-star algebras, it's always, you can find little a, so that this is approximately satisfiable but not satisfiable. Think continuous functions on 0, 1. And think A to be the identity function. It is approximately satisfiable, but not satisfiable. The annihilator is trivial. So why is this approximately satisfiable? Well, continuous functional calculus. So just look at this. So fix n, and let Fn mapping 0, 1 to 0, 1 be, I'll just draw it. So function which is linear and then drops, and this is 1 over n. Well, actually, no, let's make it 2 over n. It doesn't matter really what it is. And this is 1 over n. Right, so f is 0, this is 0. And this is 1. Right, so it's a piecewise linear function with breakpoints 0, 0, 1 over n, 1, and 2 over n, 0, and then it's 0 again. And now just apply Fn to A. Oh, actually, I wanted. Oh, actually, this was the wrong function. Sorry about it. The right function is actually easier. It starts at 0, it is 1. And then at 1 over n, it is 0. And then it's 0. So it's just this function. So Fn of A, because A has 0 in the spectrum, Fn of A has norm 1, because f of 0 is 1. And now if you look at Fn of A times A, what is this? Well, in the norm, it's less than 1 over n. Right, so because by the time A hits 1 over n, f is already 0. It's actually much less than that, but you know, we don't care. So Fn of A's approximately satisfy this type. Therefore, type is consistent. Therefore, you can realize it in countable degree 1 saturated algebra. Okay, so sorry. So at some point, I should maybe speed up, but the next one is basically more of the same. Let me just see. So what it says is that if you have A in C plus, 0 in oh no, sorry, this is that's why I thought it was more the same. It was the same one. I forgot to swipe. Right, and number 5. Number 5 is actually very similar to number 2. You see that the part of it is the same. We have these two sequences, ANs and BNs. And our C is supposed to interpolate between them, but there is an extra bit. There is a separable subalgebra D, which has this property that if you look at commutator, right, where a commutator is just a measure of how badly they are not commuting, between AN and D, for any fixed D, as n approaches to infinity, ANs are commuting with D better and better. And conclusion is that there is C, which interpolates between A's and B's, but also it belongs to D commutant. You see, none of the ANs is exactly in the commutant of D, but asymptotically they are. So this really tells you that asymptotically something happens, that at the limit, you can find, basically that you can take a limit. And you know, that there is some sort of analogy between degree 1 saturation and taking limits in certain topology. The type is almost the same as before. So you see now I don't have to worry. I can just say T of X says that AN is less or equal than X, that X is less or equal than BN for n in n. Right, so this is not degree 1 condition, but I know that it can be replaced by degree 1 conditions, so I'm not going to bother, right? So you can just basically extend definition of degree 1 type, and moreover, just add requirement that the commutator of X and D is 0 for every D in D. So again, this is a degree 1 type, because if you look at commutator, it is a degree 1 polynomial in X. And we just need to check that this type is approximately satisfiable. But again, large enough AN works, because any finite subset of the type mentions finitely many of the ANs, finitely many of the BNs, and finitely many elements of D. So you just choose n large enough so that your AN commutes with all of those D's enough, and that's it. Right, so type is approximately satisfiable, and therefore it's realized, end of the story. Right, so the point of all this is that certain arguments boil down to triviality once you get used to this. Okay, but now I would like to
Sorry. Why the D is? I mean, the D is respecting this inequality. I mean, when you want to realize approximately the type.
Which inequality? There is no for D. We just require.
Okay. Sorry.
That C commutes, right? So there is no inequality.
So the AN are the witness that the commutator is 0, is approximately 0.
Yeah, exactly. So you have ANs going up, BNs going down, and D sitting somewhere on the side, and you're commuting more and more with it. I should say here that there is a similar consequence, which is known under the name of Kasparov's technical theorem. Quite important in KK theory, use it to prove that Kasparov product exists. It is a similar statement to this one, and also very easily proved by using degree 1 saturation. And it was actually Nigel Higson's simple proof of Kasparov's technical theorem that inspired this entire thing. Basically, by just reading his proof carefully, it was clear that one can extract this notion of degree 1 saturation. Okay, but let's take a look at limitations. So here is observation of Chris Phillips that X is a unitary is not equivalent to a degree 1 condition. Right, so we saw that ordering is degree 1, that being projection, I don't know, but being unitary is not equivalent to degree 1 condition. So again, being unitary, it's certainly not obviously a degree 1 condition, right? It means that X star X minus 1 is equal to 0 in norm, and also that X star minus 1 is equal to 0 in norm. So definitely this is degree 2. But Chris actually proved that there is no way, no matter how clever you are, it just doesn't work. And how do you prove this? Well, you find a type that involves something being a unitary, so that type is approximately satisfiable, and yet not realized. And conclude that the only thing that can go wrong is that the expression that your element is a unitary just cannot be expressed in this form. So the proof depends on two properties of the Calkin algebra. First one, for any n greater or equal than 1, actually 1 is silly, I guess, n greater or equal than 2. If you have any two unital copies of n by n matrices inside the Calkin algebra, they are unitarily equivalent. So you have, let's just take M2 of C. We embed them into Calkin algebra into two different ways. Then there is a unitary, there is an inner automorphism, so that this commutes. Right? So these inner automorphisms are the form AD of U. I don't think I used this notation yet. So AD of U of some A is, oops, it is UA U star, right? This is what the inner automorphisms of C star algebras look like. So what is the point here? Well, if you have any two non-zero projections in a Calkin algebra, remember they leave two projections of B of H, which means that there is a partial isometry between them. So if you look at projections from matrix units of 2 by 2 matrices, all of them are equivalent in this form. It's actually called Murray-von Neumann equivalence. And from there, you can just basically build this unitary. Okay, I think I said this in a funny way, but trust me, this is very simple. So it's really not basically they all look the same. Okay, so they are unitarily equivalent, but you see something funny can happen nevertheless. You see, if you have, there are really two kinds of embeddings of 2 by 2 matrices into the Calkin algebra. Unital, I'm talking about unital embeddings here, that's important. So look at what is really, what are 2 by 2 matrices? Well, they're really linear combinations of the matrix units. We have matrix units E11, E12, E21, and E22, right, corresponding to the four matrices which have only one entry, and E11 and E22 are projections. You can lift those projections in two different ways. Okay, let me just tell you what that is, and just leave you because this is sort of a digression anyway. Oops. Digression anyway. So okay. So let me just see. Yeah, no, I don't think, you see, this is really, I mean, if you know what is weak X and what is strong X, the point is that weak X of M2 of n by n matrices is trivial, but strong X is non-trivial. But it is somewhat off tangent, and I'll be happy to talk about this after the class. But maybe right now it's not the right moment. I just underestimated how much one needs to say about this. So I'll just pass on, but I'll be happy to talk about it after the class. So that was the first bit. Now the second bit is, and this is why I wanted to give more details, but I'll just pass on it. If you look at the so-called car algebra, which is a tensor product of 2x2 matrices, which is also inductive limit of 2 to n by 2 to n matrices with the appropriately defined embeddings. This algebra has continued many unital embeddings into Calkin algebra, such that no two of which are unitarily equivalent. Basically, this is what I wanted to say. Each time you pass on to the next 2x2 algebra, 2x2 matrices, you can make a tiny difference. And at the end, those tiny differences accumulate, and you end up with a very different embeddings. So what this means, we have this algebra, you can embed it into Calkin algebra in two ways, many more ways, but two definitely. And for any finite subset of A, because A is inductive limit of these matrices, that finite subset approximately belongs to M2 to n by M2 to n matrices. And therefore, there is a unitary which approximately conjugates one of these representations to the other. However, at the end, this type that describes this unitary cannot be realized because these are not unitarily equivalent. So this condition of being unitary just cannot be expressed in degree 1 fashion, right? So this shows that Calkin algebra is not fully saturated, and it makes it more interesting. It makes it more complicated to work with, but also more interesting. So this just says what I just said. All right, so that was, yeah. So here is basically, I just wrote down the type, right? So here you have a type, and you see this condition can be translated into degree 1 condition. You can just multiply by x on the right and get something which is degree 1, but these two are hopeless. Yeah, so that, any questions? Maybe just leave it after. Okay, now here's another observation about limitation of the method. So definition, automorphism of separable, actually separable doesn't matter too much, of separable cyst algebra is approximately inner if there is a sequence of unitaries such that this UN, A, UN star, and this is what I, well, not I mean, this is what is denoted by ADUN, at conjugation by UN, pointwise converges to phi. Right, so for any finite subset, for any epsilon, there is an inner automorphism which up to epsilon looks just like your automorphism. Here is a similar notion, asymptotically inner. Asymptotically inner means that there is a continuous path of unitaries. So it's function from R plus into unitary group, which is continuous, such that, again, this converges to 0 as t goes to infinity, but now it converges continuously for all A. And these two are, in a very subtle way, different notions. You see, in the previous slide, we didn't have approximately inner automorphism, but we had approximately unitarily equivalent embeddings of the car algebra into Calkin algebra, which were not equivalent, unitarily equivalent. There was no single unitary, but there is a nice proposition of Phillips-Weaver, which says that if you have a separable subalgebra of the Calkin algebra, then if you have any asymptotically inner automorphism of A, it is implemented by a unitary in the Calkin algebra. Now, this looks like something that should follow from degree 1 saturation, but I don't know how to prove it. You see, model theory doesn't mix very well with homotopy. Basically, homotopy is just awkward notion to handle using model theory. Their proof uses some tricks from KK theory. Essentially, in a sense, it goes back to the proof. You use quasi-central approximate units, but in a continuous way to chop up these unitaries. Basically, one is really mimicking the proof of the theorem for countable degree of unsaturation. Although I shouldn't say that because their theorem predates countable degree of unsaturation. So one is doing the same proof, which maybe suggested that there is a better notion, which would generalize both what they did and degree of unsaturation. But yeah, I don't know. Okay, so here is another statement. If you have countably degree of unsaturated algebra, and if you take a separable subalgebra of it,
Sorry.
then this, yes.
So that unitary that implements the automorphism in the separable subalgebra, I guess that usually is outside of A, right?
Yes, because there are many separable cyst algebras have asymptotically inner but outer automorphisms. Basically, almost, I mean, any UHF algebra has plenty. I mean, for any UHF algebra infinite type, every automorphism is asymptotically inner. For every strongly self-absorbing algebra, every automorphism is asymptotically inner, but many of them are outer. So definitely, it is in the Kalkin algebra, but not in the algebra.
I see. Thanks.
Thanks for asking. Okay, back to this. So we have C, and we have this separable subalgebra A. So just to remind you, A commutator set is C, so it is all C in C, such that the commutator of A and C, my A and my C look the same. Let me just make them look different. Is equal to 0. Oh, for every A in A. All right, so just look at everything that commutes with everything in A. This is still countable with degree of unsaturated. Now, why? Well, we just fix T of X, which is type over A commutant intersected with C. So we want to translate it into type over C. So let T plus of X be T of X. I think of type as a set of conditions. So I can write union all conditions asserting that X commutes with the elements of A. And again, just choose a countable dense subset of A. And this is it, right? So because original type T of X is approximately satisfiable, it means that T plus of X is approximately satisfiable, because for any finite subset and any epsilon, you can find something that satisfies this up to epsilon, and it satisfies all of this on the nose, because realization are here. This is degree 1, and therefore T plus is realizable in C, but whatever realization is, it is going to be in the commutant way. So I'm saying this because these relative commutants inside massive cyst algebras are very frequently used. And what this means is that all of these methods can be applied to them as well. Okay, so here I'm just stating this as an exercise because I don't want to go over this in class, but I just wanted to point out it's not difficult. Certain facts about these algebras. So C is again infinite dimensional and countable degree 1 saturated. So you see, I'm assuming it is infinite dimensional because every finite dimensional cyst algebra is degree 1 saturated. And that's just compactness. It's very similar to compactness that I used a couple of examples ago. You see, you have a finite type. Actually, if you look at unit ball in the norm, of 5-dimensional C algebra, it is compact. So if you have approximate realizations inside that compact set, they are going to have a cluster point. And that cluster point is going to realize the entire type, right, by continuity of the conditions. So actually, finite dimensional algebras are completely saturated. So now, if C is infinite dimensional, then it is automatically non-separable. Right. So these algebras are huge. They are not separable. And actually, one can prove more that they are actually of a density character continuum, so that they don't have a dense subset of size less than continuum. So if you believe in continuum hypothesis, I just wasted 10 seconds of your life because there is no difference. But you know, some people don't believe in continuum hypothesis. And the continuum can be quite large in some models of ZFC, and this tells us that in those models there is much stronger statement about these algebras. Second, even every maximal abelian subalgebra Okay, I copied this from the book. Okay, I'll just put a question mark here. This may be false. This may be false. So I'll just move on to the next one. You see, these algebras are similar in many ways to von Neumann algebras. Why? Well, you see, in von Neumann algebras, you have many topologies, and you have certain compactness there. So you can frequently basically realize types which are approximately realizable by using that compactness. Many of the statements I mentioned before about these degree 1 saturated algebras, for example, that if you have increasing sequence and decreasing sequence, you can interpolate. That's definitely true in von Neumann algebras. However, these are never von Neumann algebras. Yeah, so that's actually, I'm quite sure this is false. No. Okay, how to fix it. Right, so more applications. So here is a more serious application. Okay, so here we have a discrete group and a discrete countable group gamma. Just think of your favorite discrete countable group, infinite. Otherwise, there is not much to say. So a representation into a unital C-star algebra is just homomorphism of gamma into, this is the group of invertible elements of A. Now, representation is said to be unitary if if its range is the unitary group of A. So instead of invertibles, you send everything to unitaries. We said representation is unitarizable if there is some invertible element, so that if you modify this representation in this way, you conjugate by A, you get a unitary representation. Right, so it's just basically just starts from unitary representation, and you see the other way around. You can go. If you have unitary representation, if you conjugate by some invertible, you get something that is not necessarily unitary, and it's unitarizable if it was obtained in that way. And finally, it is uniformly bounded if this norm of P, which is just the primum of norms of P of G, is finite. Note that uniformly bounded is a necessary condition for being unitarizable, because basically, this norm of A times norm of A inverse gives you how badly you can affect the norm of this. So before I go on, there is interesting conjecture about representations of groups into B of H. So there is a theorem stating that if group is amenable I'll define what amenable is in a moment. Actually, I think definition is on the next. Yes, okay, here it is. So group is amenable in the unlikely case you haven't seen definition before, if you have a so-called Fellner sequence. I'm using this notation for finite subsets. So if for every finite subset of gamma, for every epsilon greater than 0, there is another much bigger, probably finite subset of gamma. So the following holds. So delta stands for symmetric difference, and GF just stands for the translation. So it's set of GF for all F in F. So if you translate F by any element of G, you get something that you know, the difference is very small compared to the size of F. Now, this is one of many equivalent reformulations of group being amenable. Discrete, this is for discrete groups. Right, so back to what I said first. So there is a theorem that if you have a representation of gamma into B of H, if gamma is amenable, if representation is uniformly bounded, then it is unitarizable. On the other hand, if you...
Sorry,
yes.
Ilijas, what is this small g playing? It's in big G?
Oh, yes. For every, thank you so much. Yes, I forgot to write it. For every small g in big G. Thanks, Mateo. Yeah.
So if you shift by a small g, you are shifting a little. You're
Exactly, right.
You're overlapping a lot.
Exactly. So basically, just think of little g as being small, then f is much bigger, and you know, it has the property that it's robust under any of these finite shifts. The typical example are abelian groups, and yeah. So this is quite important notion. I think Z, for example. You know, in case of Z, just pick a finite set. So you just need a big enough interval so that if you just shift it a little bit by any of those, it's not going to move much. Right. So every uniformly bounded representation of amenable group in B of H is unitarizable. But if you take a free group, I think you need infinitely many generators. There is a non-unitarizable uniformly bounded representation. Okay, and degree 1 saturated algebras have a similar property to some point. So this is what I mentioned, conjecture. So it's conjecture, and basically conjecture is really if conjecture really says that every non-amenable group has uniformly bounded non-unitarizable representation on B of H. Yeah, so now before I proceed to example which uses these notions, just one bit, you see before I insisted that always all the partial realizations of a type satisfy, and realization satisfy that X in norm is less or equal than 1. Now, there was no reason for that really, except that I just wanted to be brief. You can just say that norm of X is less or equal than N. And then if you have type T of X, you can just replace it with type T of X divided by N. Right, this is all conditions are still going to be degree 1 over N. Everything is homogeneous. So you just need to decide what is, where you want your X to sit, just what N ball. I'm just saying all this because it's going to be easier to talk about N ball in the next proof than about 1 ball. Right, so yet another relaxation of degree 1 saturation. So here's proposition. Suppose that gamma is a countable amenable group, then every uniformly bounded representation P of gamma into unital countable degree 1 saturated C algebra is unitarizable. Right? So these algebras behave like B of H in this sense. Now, there is an obvious type. Right? So you have your P of G for all G in G. And what you want, well, you want that X inverse P of gx, you want this to be a unitary, which means that this times this star that this is equal to 1. Okay, but now you can simplify this a little bit, and this runs over all G in gamma. You can simplify this a bit, but still it is not, it doesn't look like a degree 1 condition. So, but there is a little trick that one can use to basically write non-obvious type, which has the property that realizing that type gets us exactly what we want. Right, this obvious type is not degree 1. So here is the non-obvious type. First, we say that x is equal to x star, and remember this is just an abbreviation for x minus x star norm is equal to 0. X is less or equal than norm of p squared. Remember, p is uniformly bounded, so this is some finite number. And now also we want x to be bounded below by norm of p to minus 2. And here is our condition. P of g x, P of g star is equal to x for g in g. Right, so instead of the obvious x inverse P of gx being unitary, we have this. And we'll have to see at the end why this is enough, but this is what we want, right? So this is the degree 1 type, at least modulo the standard tricks that I learned so far. And first, we want to check that this type is indeed approximately satisfiable. Okay, and for that, we use this little device. So fix a finite subset of the group gamma. And look at this. So this is average of certain expressions. So for each f in this set H, look at P of F star. Now note, P of F star is not the same as P of F inverse. It is just the adjoint. Right, so what can we say about this element? Well, it is positive because each one of these is positive. Also, in the norm, it is less or equal than the norm of any of these, but that's less or equal than the norm of p squared. Right, so this is p and p. Also, from below, it is bounded below by norm of p to minus squared. Why? Well, because each one of these is invertible.
Sorry to ask triviality, but why pi f times pi f star is positive? It's not normal, no?
No, it's self-adjoint. Well, if you have any a star, and this is how we define positive elements, right?
Okay.
Define them as a star a, no, not a star, but just replace them. It's the same thing, right? Yeah.
Mm-hmm.
Was that a question or somebody didn't know themselves? I think. Okay. Right. So why this? Well, look, what is the norm of P of F inverse? It is at most norm of P, because this is the representation of a group, and because of that, we have that this inequality is satisfied. Now, this is not going to be satisfied, not on the nose, but that's where the amenability comes into play. So let's move on to the next slide. Right, so we checked.
Sorry, can I ask?
Yes, sure.
You said little g is in big G. What's big G at this point?
Oh, big G is gamma. Sorry about that.
Oh, okay. Thank you.
Yeah, G is gamma, right? So that's Greek. Yeah. So yeah, thank you for pointing it out. Yeah, I hope there are no other typos. Okay. Right. So okay. So we have this guy. It satisfies all of these conditions. This one we want to satisfy approximately. What is? How do we do that? Well, let's just first observe this that P of G, H sub H P of G star is H sub GH. Right? So GH is this translate of our little set H. So why is that so? Well, look at this. So P of G times 1 over size of H sum over all F in H, P of F star, and now P of G star. Well, this is a group homomorphism, right? So P of G times P of F is just P of GF. So this is 1 over size of H sum over all F in H, P of GF times, and now here we have P of F star, P of G star. Well, when you just remember how the adjoint works, this is just P of GF star. So by a change of variables, indeed, this is just HGH. All right, but now what if I have some finite subset F of my group, and now, no, actually it was G first, right? So if I have finite subset G of my group, and now I also choose some epsilon greater than 0, and then I choose a bit bigger finite subset F, such that GF symmetric difference with F, cardinality of this is less than cardinality of epsilon times F. What happens then? Well, if I look at HF, if I conjugate it by any P of G, here G is in G, well, this is going to be H sub GF. But now, if you look at the way that H looks like, what is HGF minus HF? Well, this is going to be within epsilon times norm of P squared. Norm of P squared because H, okay, let's put it right this way. Epsilon times norm of HF times HF. Right, which means that at approximately arbitrarily closely, I get this here satisfied. Right. So for every finite subset of the type, you just take this set of elements of the group which are mentioned in that type, pick appropriate Fellner set for the epsilon that was given in advance. From there, you just take a look at this H sub F, and that's H sub F is going to satisfy that part of the type up to epsilon. So the type is approximately satisfiable, and therefore it is okay. So actually, this is in my slide. So I was talking, but so this is what I said. So let A be H sub F. Oh yes. Just shouldn't be doing this right here. Okay. right? So this type is approximately realizable, and therefore we have an element which realizes the type. So let A in C realize T. Now, what do we have? A is self-adjoint. Okay, that wasn't required, but actually it's known that if you can unitarize representation, you can do it by a self-adjoint element, even positive element. So A is less or equal than norm of P squared. It is greater or equal than norm of P2 minus 2. Now, you may wonder, why did we need these conditions? They are really not being used. Well, the point was that it is not enough to know that every finite subset of type is approximately realized. You also want to have bound on the norms of those realizations. Otherwise you can just write a type that norm of x is greater than n for any given n, and you just would never have it realized. It just has to stay inside some bounded norm ball, and that was the purpose of this condition, and this one here. And finally, we have that P of G times A times P of G star is equal to A for every G in gamma. So this is gamma. Okay, so this is not quite what we wanted. All right, but let's see, what do we have? Well, A from here is positive. So by continuous functional calculus, we can form square root of A. So let B be A to 1/2. And I claim that B unitarizes this representation. The claim is that this G goes to, actually I don't even have to write B, I'll just write A to 1/2. A to 1/2 P of G A to 1/2 is a unitary representation of gamma. Right, so there are two things to check, that it is unitary and that it is representation. Okay, so first, so why is A to 1/2 P of G A to 1/2 a unitary? Well, you just multiply it by its adjoint and keep your fingers crossed that it is going to be unitary. So it's A to 1/2 P of G star A to 1/2, right? So what do we have? A to 1/2. Here we have P of G A, P of G star A to 1/2. But now what was P of G A, P of G star is equal to A. Oh, sorry. What did I do? I did something wrong here.
Should one of those be minus 1/2?
Yeah, one of those should be minus 1/2, of course. Thank you. Yes, right. So of course this wouldn't be representation. Thank you. Yes. So this is minus 1/2, and this is minus 1/2, and this is minus 1/2. Right. So this is how it works, and now it's going to work out good. Right. So this here is equal to A. So this is indeed 1. Right. And similarly from the other side, also you get that A to minus 1/2 P of G A to 1/2 star times A to minus 1/2 P of G A to 1/2. This will again be 1. Right. So it's unitary representation. It's unit. I mean, all of these are unitaries, and to check its representation, it's very similar. So if you have A to minus 1/2 P of G A to 1/2, times a to minus 1/2 p of h, a to 1/2, these two cancel, right? And what you get is a to minus 1/2 p of gh, a to 1/2. Right. So indeed, we have unitarized representation of this. Okay. So this was that one. Any questions? All right. So now here is another difference between these algebras and von Neumann algebras. There is the previous theorem works only for countable amenable groups. So even this abelian group with direct sum of z mod 2z, for set theorists, this is really a finite subsets of aleph 1 with respect to symmetric difference as the operation. So it's definitely something that set theorists see a lot. So there is a representation of this into the Calkin algebra, which is uniformly bounded and not unitarizable. And it has interesting applications. I don't want to go into that, but there are applications. And another point that I'm not going into, entire chapter 14 of my book is about examples like this, basically interesting peculiar pathological objects sitting inside different massive algebras which have cardinality aleph 1 and which show that this whole story stops at aleph 1, at the first uncountable cardinal. Right, so I only have time to mention two more examples of applications of degree 1 saturation. So here is one that I like a lot. So let me just say where it comes from. There is a theorem, actually it's lemma, I think they call it lemma, of Brown, Douglas, and Fillmore, which is a special case of this here. They proved it inside the Calkin algebra. And you see the power of this is that you just prove something and it works in Calkin algebra, in all sorts of other algebras. You just have to prove it once. So what they prove is this. So if you have A in the Calkin algebra, such that spectrum of A is 0, 1, and A is self-adjoint, then there is an element. Okay, I may be misstating their theorem. It's basically, this is a, I'll just say what is the point here. Okay, maybe this is not the whole theorem. So then you can find an element C, which is also self-adjoint. Actually, it's even positive, which has the property that it. Okay, so that there is, sorry, there is C in Q of H, which has the following property. So if F is in C0, 1, if support of F is subset of 0, 1/2, then CF is equal to F. Right, so it acts as a unit, at least on this bit here. So by support, I mean points at which F is not 0. And on the other hand, if support of F is subset of 1/2, 1, then CF is equal to 0. And so somehow C acts as if it is what you obtain from A by a discontinuous functional calculus by a function that is 0 from 1 from 0 to 1/2, and that is 1 from 1/2 to 1. right? Not literally, but it's good enough. And also, I forgot to say that C commutes with A, and you can get all sorts of other requirements that if you have some separable algebra which commutes with A, you can make sure that C commutes with it and whatnot. So this is generalization of it. And the point is that proof is very simple, really. Once you understand the statement, you just write down the type and check it works. So C is counted given saturated. A is a normal element. So A stands for this A here. There is a separable subalgebra, which is subalgebra of the commutant of A in C. And there is open subset of the spectrum of A. That open subset was really this interval from one, I mean, you're just removing 0.1/2. And then you have bounded continuous function on that open subset, right? So G doesn't have continuous extension to the spectrum of A, but it's continuous on this open set. And then there is a C, which commutes with everything that it's supposed to commute with. And it has the property that for every F in spectrum of A, in continuous function on spectrum of A, whose support is subset of U, when you multiply C with F of A, so this is this, then you get a GF of A. G was this function that you used to construct C, right? So if you just take G to be this function here, constant 0 here, constant 1 here, you get special case of this lemma. But in general, this works for arbitrary continuous function on any open set for any normal element. And also extra, if A is self-adjoint, then you can get, no, not A. If A is self-adjoint and G is a real valued function, then you can get C to be self-adjoint. Yeah, so proof is very straightforward. I'll just mention one more theorem whose proof is not straightforward at all. And then I'll finish. So one more definition, C-star algebra is essentially non-factorizable if it's not isomorphic to tensor product of two infinite dimensional C-star algebras. So emphasis is two infinite dimensional C-star algebras. Because, for example, B of H is tensor product of n by n matrices n B of H. So it's that's something else. Now, B of H is an example. Which may sound awkward, but you see, because B of H, tensor B of H, it seems like it should be B of H. Well, it is B of H if you're talking about von Neumann tensor product, right? If you're taking product as defined in category of von Neumann algebras, yes, it works. In category of C-star algebras, B of H tensor B of H is not B of H. It's something weird. And another example is free group von Neumann factors. These are free groups, Fn. But very nice result due to say it is that every, actually, okay, so since he likes SAW star, we proved before that countable degree of saturated implies SAW star, so it's actually stronger theorem. Every SAW star C-star algebra is essentially non-factorizable. In particular, the Calkin algebra, you cannot write it as tensor product of two infinite dimensional C-star algebras. And this was actually a question of Simon Wasserman that started the entire thing. The proof uses a bit more, it is more complicated than the proofs that are presented today. It is in the book, so I'm not going to go over it. There are some interesting questions there as well. And what is this? These are my slides again. This app is, every time it copies slides 2 times. I have no idea. Anyway, so that's all I wanted to say. So thank you. Any questions? I can go back to that question about MNs if anybody wants to listen. But I guess you maybe have some more interesting questions. Oh, sorry. There was something in the chat. I was completely overlooking the chat. Sorry. My apologies to Pedro. Let's see. Oh dear. Sorry. So is there a standard strategy to show that some property is not equivalent to a degree 1 condition? So this was asked 1 hour ago. My apologies. So if I overlook your question, please feel free to unmute yourself and ask it. Right. So now I'm not sure what was the timing, because I did present some tricks. I mean, there is nothing non-trivial. Basically, you just write down a type involving that property and prove that in some degree one saturated algebra, that type is approximately satisfiable but not satisfiable. We are not aware of anything better than that. So I'm sorry that I'm answering this 1 hour too late, and also that my answer is kind of crappy. Let's see what Pavel asked. Shouldn't C-star tensor product be specified? Yes, that's correct. That's correct. But no matter which one you specify, it's not going to work. Yes. This I wanted to avoid this question, but in case of C-star algebras, there is more than one tensor product in most situations, unless you're dealing with nuclear C-star algebras. So the theorem, full theorem is that it cannot be presented as any kind of tensor product of two infinite dimensional C-star algebras. I hope this, I guess this is what you meant. Right, so, but there is another question. Again by Pavel, sorry, yes, thanks. So I'll read now second question. I've got a question maybe a bit unrelated about other massive C-star algebras. Are tracial norm ultra powers, yes, and tracial completions, are these even massive counter saturated? Effective passes relative commutant seems really useful. That's correct. Right, so if you look at tracial ultra powers, they're actually fully saturated, but in a different language. So you don't use norm, operator norm. You use L2 norm, right, which is what you formed. And there you have actually full saturation. So I'll say a few more words about this, but basically you can take conditions in which you have norm of arbitrary polynomial of any degree, and you can also have quantifiers sup and inf, and you have full saturation for that. So there is a bit more about it in chapter 16 of my book, but I'll say a few more things about that. So, oh, I see. Okay, so Pedro clarifies. Okay, so it was an excellent question because you sort of guessed what I was going to do next, but still sorry for overlooking it. So yeah. Any other questions? Okay, so if there are no questions, then thanks for coming, and I'll see you on Monday. Yes. Okay, thank you. Yes.